What about you? How's your weekend?
Uh, Ups and downs.
Ups and downs?
Ups and downs.
Yeah.
Yeah, I flew up to see some family, who are not doing well.
Oh, no.
And then decided to do some irresponsible things,
Oh,
like, go to Coachella.
oh, you did?
I have a married best friend and he's got 2 kids. And so when he says that him and his wife are both free, then you say, okay, fine, let's go.
Okay.
Cause the chances that you ever get to hang out with both of them is very low, you know?
Oh, good. Okay. How do you know him or do you know that?
It's actually my college roommate.
Okay.
So with undergrad, I'm not gonna tell you how long ago that was, but it was a long time ago.
Oh, okay.
And so I've known him for.
Oh, okay. Where'd you go? Where did you go to school? What did you?
Santa Cruz.
Santa Cruz. Oh, okay. Uh,
Which I recommend people visit, but no longer do I recommend folks actually go there for, school, only because of how poorly they're graduate students.
Other graduate student.
Yeah, the budget that they pay them is quite small compared to the cost of living there.
Oh, yeah, I'm just Santa Cruz. Then.
Oh boy, if only I could teach this class while sitting. That'd be perfect. I looked at my, to watch this.
Yeah.
I walked 25 miles.
Oh, shit.
Personal record for steps, 50,000 steps,
Oh.
all from 1 p.m. onwards. In 100 degree heat. And in the dust. So I am less than stoked. I know Rolando, you're probably thinking about this. Where's the homework?
Yeah, I was.
That's my bad.
Well, to be fair, over the weekend, I was at UCLA, so I can.
Good.
I wasn't gonna push it. It was like, hey, you taking your time.
Okay.
I'm working on
All
it.
right.
I'm still working.
If we're all on the same page, I'm okay with that. So here's what I'll do is I'll post it today.
Okay.
And if you want to turn it in by Wednesday, that's perfectly fine. But if you wanted to turn it in by next Monday, I think that's more appropriate.
Okay.
Basically gonna be some of the stuff that we've already seen. So just looking at the derivatives and whatnot. And then hopefully today we'll talk a little bit about branch cuts and singularities. I think we're gonna skip over some sections like conformal mapping and go to how do you do integrals in this space. And hopefully that'll set us up well, I think, for the next 2 weeks to do functions of a complex variable. Questions before we get started?
Did you record and post the last, did I miss last one? I just last the past Wednesday. Or,
I think it's posted.
Okay.
But if it's not posted, let me know.
okay.
That could be another thing I forgot.
What?
Do you mind not on this one?
Yes, I did. Thank you. Thank you. Okay.
Okay.
We're ready, yeah.
So what were we talking about last time? We were looking at, we saw power series. And we saw that the exponential could be written as a power series. Do you remember that? We wrote
Yes.
this.
Yes.
We wrote that the exponential of C is defined as right?
Yep.
And that was the same for real numbers. This is how we defined it. Using a standard power series. We're talking about, say, e to the x. And then we showed, for example, that you could take its derivative as normal. We saw that it was singular valued because the power series was one that we examined first, singular valued, right? We could wake the brain up here. Want to do a quick example just to get our brains working?
Yeah.
Okay. Can you show me That's true enough?
Yeah, that's good.
How are we approaching this?
I'm writing out the exponentials. And then they're multiplying them together. And then. Or,
I started with the left hand side.
Yeah, you started writing out these in terms of power series?
Yeah, improvement powers.
yeah, right. The other thing too is, we can just write it as e to the z, or can you do that?
Yeah, that's equal power.
Yeah, so you could write e to the power of z, but of course, that's, you know, choosing the information that we have already.
Okay, that's why I wasn't sure, okay.
So it's right, you write this one out as a power series. So what does that look like?
1 plus. Oh, you're gonna write the whole thing.
Yeah. So we're definitely not gonna write the terms out here.
Okay.
Okay, that's one.
Yeah.
And the other one, the same, but with, very good.
Okay.
Okay, so that's interesting, right? Because you have a sum times a sum. So what's that gonna end up looking like?
What's it gonna look like? It's,
Well, they're both over like the same thing with like the same condition.
yeah,
Okay,
like, can you factor out the infinite factorial?
yes, we might wanna do something a little different here. Maybe we call these different letters. Because we wanna identify that they're two different sums, right? Let's call one of them R, and one of them S. Okay. And we're gonna have coefficients that look like. R, sorry. Z1 R times Z2 S. Right?
Yeah.
Okay. What's the coefficient then of that? Product?
The coefficient,
Yeah. You see how these have a coefficient in front of them?
oh, the 1 over, it would be r factorial, s factorial?
Oh,
Okay, so that's already looking much better, right? And then from the definition that we just used up there, we know that the right-hand side, this piece is supposed to be, what is that supposed to look like?
it's like. Well, Z1 plus Z2 to the power of it.
You do like a substitution? Like a z
Yeah,
plus
well, so
one?
now what we need to do is, we have something that's of this form, we have something of this form. And what we're gonna be looking for in particular are the coefficients of Z1 and Z2 to those powers. Where you're matching them up using the. Remember when we were doing permutations and combinations? We had that big C. C choose one of all the different permutations we can have. They're multiplying sums together. you're gonna have varying terms, right? So for example, if these are both, let's say the sum only went to 2. Then you'd have 2 copies of this times 0 copies of that, plus 1 copy of this times 1 copy of that, plus 0 copies of this times 2 copies of that, right? That's the quadratic formula.
Yeah.
So of course, we'll have to find all of those coefficients and then match them up with the ones that are up here. Okay. And you can do that. I'll leave that as an exercise to you, but it looks like this. This one in the front. The 1 over r factorial s factorial is actually equal to r plus s. And this is that big C that we were thinking about before. 1 over r plus s. So this is r plus s, choose s. From the different ways that we can take unique combinations from the two. Does that make sense? Whew, okay, brains a little warm maybe?
Yeah, yeah.
Lost or not lost?
It's definitely different. I'm not used to doing the math with a little,
Yeah.
some summation symbols.
Yeah, and these ones too, right? The important thing to keep in mind is how does it look for the whole series? Right? So you can start at the bottom, you can start at 0, work up 1, 2, 3, 4, 5, and you'll start to see all of the terms. But since the product of both of them, then every one of these terms has to be multiplied by every one of these terms and vice versa, right?
Okay, okay.
That's why you need this. Okay, so this led us to a discussion of the complex exponent. And we wrote something like. We wrote something like this. A to the z. Remember that one? How do we write that?
In terms of power series.
Not. In terms of the exponential.
Yeah. So like, wouldn't it just be like exponent x plus r y? Isn't that like?
Sure, but we don't need to go there yet.
Yeah.
We'll do z right now.
Yeah. Oh, but just c.
Z natural log of A.
Very good. So z ln a, right? If a equals e, then you get back inequality. Right, this side on the left-hand side is e to the z, and we already showed that.
Oh, cool.
And ln of e is,
Wait, what?
what's ln of e?
Oh, that's.
Just making sure. Okay. So, we showed, for example, that you can have an exponential z. And you'll have a modulus. It's gonna be talking about how large it is. And the argument, we're gonna be talking about where it is in that real space, in the unreal space, right? So we think about it as drawn in some complex plane R, X, I, Y. Right? This is the modulus. And this is the argument. That make sense?
Okay. The argument is that data.
Yeah, well, and we can define it in a number of different ways, but in this particular circumstance, we need to think about it in the context of this 2-parameter space of X and Y. Right? X is the real part, Y is the imaginary. But the modulus tells you how big, it's not really a vector, right? So I'm trying not to use those words. But in your mind, you think of it as though it's a vector, even though it's just a number, right? It's a complex number with both a size and a direction in the real and imaginary planes.
Like a basis vector for the coordinate system kind of thing.
Right, this is not a coordinate system. Right,
Okay.
it's not a coordinate system. So this doesn't have a direction, but it tells you how real or unreal the number is. right?
Okay, that's called the modulus.
No, that's the argument.
That's the argument.
Argument is how real or unreal it is, right? Because of course, the number is fully aligned in X,
It's fully real.
fully real. If it's fully aligned in not plus IY or minus IY. Right? Okay. We're chilling?
Yeah, modulus again, one more time, that's
That's just how big.
that's how big, okay.
How big's the number? Okay. And then I can orient the same size number from the real to the imaginary. Okay. We worked through that one. We saw that sine and the hyperbolic tangent and all of those trigonometric functions, they can come from that and they can have an argument as well. So let's now talk about the natural logarithm. So let's start by talking about the inverse of some exponential. So let's imagine that there's some exponential of W, which is going to be equal to Z. We just talked about this when we talked about the exponential, because we found that when we look at the IY component, there's an argument where as I go around the real or imaginary, if I keep adding plus 2 pi, then I can get a multi-value function for W, right? So we know that there's going to be multiple values for it, right? So we're going to have to use some special words here. We're going to learn those words. So let's first look at Z. Let's define Z as R exponential I theta. You love that, right? So what's R?
Would that be equivalent to modulus?
R is our modulus. And what's the I theta?
That's gonna be your argument.
Argument, right? Okay, and then the thing that we see here, of course, is that the exponential I theta, right? This is where we get that multi-valued ness, right? Okay. So now let's take a logarithm of this. Let's write W, which would be the log of Z. I guess I should put it more careful here. Let's write it like this. And I'll change it where it's appropriate. So that's the log of Z. Right? And I'm going to take the log of this one up here.
Log or natural log?
Well, I wrote it like this so that it's general, and then I'm going to write the natural log when it's appropriate. So that'll be just this one here. So it's ln of, how do I do it up here?
The R exponential I theta.
Yeah, so the R first, right? And what happens to the I exponential?
Oh, yeah, so it's I did it.
How do I add? What do I?
Oh, R, I did.
It would.
What?
It's saying
Oh,
Plus.
Plus.
plus,
Right, remember multiplication becomes plus, so now I do plus what?
natural log, right?
Nope.
I
Just I did,
Yeah,
right?
'cause it
The
comes back.
natural log is in the X.
Yeah, okay.
Good. Okay, so I theta. I'm gonna make this general. Okay, I'm gonna add plus 2k pi. Make sense? Why do I do that?
Okay, for each rotation.
You get your same answer. And so we will typically call, this is a multi-value function, obviously. We'll call, when you drop this piece here, we'll call that the. Okay, when you drop that part and you're not looking at multiples of k, right, when k equals 0, that's considered the principal value of the argument. That makes sense? Yeah, So over here, if I drop k or I set k equal to 0, then the value that you have here is what we call the principal value of the target.
Okay.
Okay, then everything else, right? They don't have different names. But okay. So we would say the principal value of LNP R plus I theta when theta is greater than minus pi and less than. Cool. Okay. Um. Yeah, let's try to find some roots really quick. Use our brains. So we can say something like, now that we have the complex exponential defined and the natural logarithm defined for a complex variable, we could say something like this too. T of z, right? Not very different from what I'm about right over there, is the exponential of z ln t. Okay, I've just rewritten that.
Great, great.
Since ln t is multi-valued, right? So is this definition. Is that clear? Since ln t is multi-valued,
Yeah.
then this implies that this is multi-valued as well.
Okay, okay.
Okay, so its principal value is obtained by using the principal value of ln t. That's right there, right? So that would be the same principal value, right? Okay. So now the question is, have we talked about how to find roots? What a root is?
No. At least we can complex variables.
Yeah, so not like square roots, I suppose. I don't know if we want to spend time on it. We might want to just talk about branch cuts so that we can get into contour intervals. I don't really know how long this whole section is going to take.
Okay,
So we're winging.
all right,
We're winging.
follow along.
So we see that there are these multi-valued functions defined in this R space. And it's important to define something called a branch point, which would be a location where you can have multiple values for the same function. So you may have seen these before. We consider them like singularities, right, where they go to infinity. A branch point would be different from a singularity in that you have a multitude of answers at the same location. Right. Okay. So let's consider the multi-valued function f of z is equal to z to 1/2. First of all, is that a multi-valued function? I mean, I know I just said that,
Well,
but.
yeah, because you're gonna have the negative answer and the positive answer.
Okay, yeah, even that one alone, right, for a positive number, you still have a multi-valued function, right?
Yeah.
So then you add in the fact that it's real and imaginary, right?
Okay.
Bucks the open good one. So this one we already know, right?
Yeah.
Multi-valued, no problem with that. Let's express z as a r, right? We're gonna write it as r exponential times theta. And then we'll apply this. So this is written out.
Exponent z natural log 1/2.
Natural log.
Oh, wait, I mean, 1/2 natural log of z.
So let's try this one.
Wait,
This
you're
one,
talking
let's
about-
try this one on here first, on the r, right? Let's do r 1/2. How does the 1/2 get into the exponential? Does it?
Exponential I theta.
Right. Right. So we don't have to worry about the logs yet. Okay. And it's very clear now, of course, that it's still multi-valued, right? Because that argument just churning and flipping over and flipping over. Okay. So the question is I'm not gonna be a very good drawer of these, but they may be helpful. So actually that'll work. Let me use this one really quickly. So let's imagine in this space over here, I have f of z equals z 1/2. That exists in this real space. And I'm gonna point out some point here, okay? And then I'm gonna draw a contour. And this is some path that I decided to walk in this space R. Will I encounter the multi-values of z to the 1?
Like just in that path.
Yeah.
Does it depend on the modulus? If the value of the modulus for z.
Well, the way that we're going to think about this is right. Here's the location.
Yeah.
As I walk along, the R, right, gets smaller or farther, but smaller as I get closer and larger as I get farther, and theta moves from here out to here, right?
Yeah, that's
So you're talking about it going more imaginary, more real.
Yeah, I mean, I'm staying on the right-hand side of positive x.
Yeah.
I'm staying in the upper quadrant of IY. And as I walk along that path, both the argument and the modulus are changing, right? Because you want to think about this line as drawing out, right? So it
Yeah.
looks, wish I had like a little ruler, right? But it would do something like this, right?
Yeah.
Okay. And so my question is, looking at this here, will you encounter the locations where z is multi-value? Why not?
You're only in one quadrant.
Sure, but why is that a problem? Or a good thing?
If you put in like, maybe, believe it, you'll get you're doing, process.
Say that again? What's the last sentence you said?
You haven't crossed over like.
You haven't crossed over. Okay, so when we say crossed over, we really are identifying locations, physical locations in the space, right? That we would have to pass. Right? So we will talk about something called a branch cut. Right? Like for example, if I were to draw, I'm gonna draw the same thing again. Here's my contour interval, or sorry, just the contour.
I thought it was a circle.
It's kind of a circle. It's a bad circle. The nice thing about when you're doing contours, right, is they don't have to look like circles anymore, so you can get away with all of the wheels are supposed to be there. Okay, so, this contour, does it include a place that's multibound? Where? Here? What's wrong in that region? Okay, all right, let's think about this a little harder. What are the locations where you're getting multiple values of the same object?
Like,
Is
the
it,
continuities.
is it the R? Is it the argument?
Always where,
Yeah, what about this function is giving you?
It would be the, it would be the argument.
It's the
It
argument,
would have to be
right?
the, yeah, cause
Because
the
this one here is a single value.
single value.
So the argument is what's giving you multiple values. So where are your multiple values? I mean, think about this in the context of a sum of sines and cosines, right? If you had a sine, where would your multiple values be?
oh, like in the theta.
Yeah,
Yeah, it's like as you're going around that.
so look at this
Theta.
one, I theta over 2.
Oh, okay, because like, if you have like different values of theta, you can get like repeating values.
Exactly. Yeah. Okay, right? So you can create what's called a branch cut. Okay? And what you would say, and this is just mathematician doing mathematician stuff. Okay, so maybe I'll use it as a topic. Okay. So this will be my branch cut. And what I'm doing there is I'm basically bisecting the x line, x equals, or sorry, the y equals 0 line. And I'm saying that if I'm on this side, I'm gonna use the value that it was approaching this side. And if I'm on that side, I'm gonna use the value that it was approaching this side. And at the branch cut, I'm not gonna care. Does that make sense? No, it doesn't make sense? Yeah, okay, so for a branch cut, you'll notice that I'm cutting the 0 line. Right? I'm cutting it sort of like I'm making like a choppy shape. So if I approach it from this side, I'll take the value that it was going that way. And even if I'm on this side, I'm gonna use this value. But if I'm on this side, I'm gonna use this side, right? See? It's just like an instruction thing. Okay. We try one.
Yes.
Yeah, okay. That seems very weird, right? Okay, so let's simultaneity of that guess was pretty good. Let's try yeah, what do you do with that? Okay, so the first question is, can you find R, let me ask two different questions. But it's not too leading. Is this multi-valued?
It should be,
Why?
could we have that z to z squared?
Yeah.
Z
Square.
Squared.
Z squared, the Z, what part of this is the sketch part?
Square.
It's the square root.
Yeah, square root.
The square root's probably gonna give us trouble here. Necessary, the square root may or may not, right? Okay, so we think this will be multi-valued. So what are the branch points? How would we find them?
I guess we have to find the root of g.
Yeah, so let's rewrite this in a couple different ways. How would I rewrite the interior version?
Well, rx I theta.
Sorry, just the polynomial in terms of polynomials, not using R's yet. What's another way to write Z
Like-
squared plus one?
Z plus one, Z minus one, kind of, or is it,
Why?
Z plus I?
Is that true?
Z minus I z plus I.
Write it out. Let's see if it's true.
Yeah, okay, yeah, that's true.
Fun little trick, right?
Yeah.
Okay. So let's just imagine a different function. We just talked about this one here. And we said it has a branch point where?
Actually, did we talk about the branch point?
Well, it's gonna, so the branch points are the points where you're gonna get multi-values, is that like a line where you're gonna be finding those multi-values?
Yeah.
Okay.
So the branch point, z equals 0 also has multi-value. Right, so if z equals 0, then of course, whatever argument you want, you can run that up, right? And then we made a cut along the y equals 0 line, right? You have, let's say this different. Let's write this over. Branch point is equal to 0, right? We said that. So where's the first branch point for this function?
This one, not that one, right? That one. So it'd be 1, -1, right? Cause it'd be Z 0 squared plus 1, so this is 1, square root of that is 1. But the square root of that 1 could be 1 or -1, is that what you're talking about?
Well, I want the argument to be 0, because that'll be the first. I or negative I will be the places, right?
Okay, great.
The places where that becomes 0. So I get 2, I get 1. Let's write down all the branch points. I, negative 1. Cool, those ones are for free. Not really. And now we have to do a little bit of funny math. Let's call this thing here. Call this R1 exponential I theta 1.
Okay.
And let's call this thing here R2 exponential I theta 2. Is that okay?
Okay.
So then we can rewrite this top piece. Let's imagine that I wrote this better. And the square root of R1 times R2 and the exponential of
beta.
Did a one, yeah.
Oh, plus theta two.
Right.
Yeah, because I put that.
Whew, rough. Okay. So now, let's draw some space, some R, and we'll see, how the function changes as we go across a loop. Let's, I'll do down here. Like this. So what are the first two branch points? I said I and minus I, so put one here. I, and down here, it's minus I.
Okay,
Okay. And let's go all. Right? How do I revise that like that? Point Z.
okay.
Makes sense or no? Okay. Okay, so if you. Let's say I do the contour out here. What is the value of F of Z?
Like assuming that like the point C is like on the contour.
Yeah, it has to be, right?
Yeah.
So,
Oh, okay, so it would be negative I when it's below like the x-axis. And then anything above the x-axis you use positive I, is that correct? So I'm counting this.
What do you mean by that?
Okay, so like. Yeah,
Now remember, this is just I times y1.
I think by one.
This is I times y minus
Okay. So then if we're gonna have a point C here, then like it's gonna be. It's in this direction, so if we start like right here, kind of goes down, this decreases, and then like this little region. I was talking about like this little path,
1.
this is where it's like, I guess R2 is closest to something than R1. Or how should I say that? Z is closer to negative I. So I was thinking like maybe like this x-axis might be like a branch point or something, but I kind of see the logic.
I see, okay, so we're still thinking about it in the context of this one, right? Thinking about a branch line that was on the X origin, or sorry, on the X axis. This one won't have that same, solution. And, the reason for that is if you take any point that's not on a branch point, there's only two branch points here. Any of those points along the branch point, they're gonna be unique. Why is that?
they have different moduluses, they're different,
Yeah, they have two
Arguments.
different data, right?
yeah.
So as I go around this circle, as long as it doesn't enclose the range points, you're good. Okay? So what happens though, if I enclose, say Z equals I, say I enclose this one.
Okay. There we go.
Now we're going, right?
Okay, yeah, I see that now. Cause when that modulus is on that yi axis. I guess there's definitely two different answers
Right.
for the same.
For the same value of theta. Right? So if it includes this one, but not this one. Then you automatically get theta one, will have a branch point where it goes theta one will be equal to theta one plus two pi. Right? And because of the way that it's written, then f of z will be equal to minus f of z. Right? Because it's theta over two. Right?
Yeah.
Okay. Similarly, if you flip that around, you put one on the bottom there, same explanation, same reasoning. Okay. But interestingly, if you do this, you do both branch points. You get the contribution from this one and the contribution from this one, but they cancel out. So f of z equals f of z.
Oh.
Okay, so. If I understand this correctly, let's say contour one is that one with like little like mountain. Like peak, right, all the way to the right.
The one that doesn't include either branch.
It doesn't include either branch, so that's a single value. So, and then if you were to have the contour that's only encapsulating I1 or positive I.
Yeah.
Then that is when you have a branching, like it's.
Well, it encloses the branch point, right?
It encloses the branch point, so that means you have multi-values.
You have multi-values because when you look at the argument, it is multi-value.
Okay.
Right.
Okay, and then that one that final contour that encapsulates everything. It's like the contribution of, the each branch points they cancel out,
They happen to cancel.
they happen to cancel.
It's not generally true,
Okay,
but in this case, they happen to, right? Because this one contributes plus two pi, this one contributes plus two pi. And so you from f of z, you get f of z again. Whereas before, when you include only one of them, you go from f of z to f of minus f of z,
okay,
right? Switch the. Okay, and you could draw those branch points if you want, they're a little boring.
They're a little boring.
Yeah. So here's minus I. Here's I. There's two ways to write it. You can either make a branch cut here. Like that. Or. I'm gonna get the other one. Yeah. If that doesn't look like fake math, then nothing else will in your life, right?
Does that look like fake math?
Yeah, that's gotta be fake math, right?
Yeah.
That's barely even math. Okay,
Okay.
okay, so we have about 30 minutes left, so I think we should talk about singularities, unless there's other questions about this.
No, I'm gonna go over this one, but that, I get the concept.
Okay. Oh, so what is a singularity? Have you heard of that word before? That letter? Those orders?
Yeah, that's where the,
single, I'm sorry, single coordinate point where there can be like multiple values and that blows up there.
Yeah, in particular, I like the blows up there, right? Single point blows up, goes to infinity. We will say, generally speaking, we want to use some good mathematics mumbo jumbo. Okay. Let's write it, you know, we'll try to be very specific with our language here. We talked about the importance of defining things like whether or not it's analytic, and whether you can take a derivative and everything else, right? So we say that a function, if it's analytic everywhere, that right there. except in a neighborhood containing Z0. Okay, and there's no other singularities? Then we call that an isolated. Branch points are not isolated singularities.
Okay.
Does that make sense what that would be?
Because you're talking about, because it's in a line like that.
No, just the point. So like these are the branch points. These branch points are not isolated singularities.
Or because there's other singularities, there's other branch points.
They're branch points. Okay. So the most important type of isolated singularity is called the pole. Okay, so what does the pole look like? Generally speaking, the pole has the form, you will have seen this before. F of Z equal to, doesn't matter what's on top, some function G of Z over. It also does not matter what's on bottom. This is all that matters.
So you get a pull in and Z naught because that function goes to zero to floats up.
Oh, yeah, if Z equals Z naught.
And this has a lot of baked in assumptions, right? So this of course assumes that G of Z is analytic everywhere, and therefore that F of Z would be analytic everywhere. Right, because that's the first part of what we're talking about here. We want to assume that N is a positive integer. I should probably say real too, but I think that's inferred. Oh, and that it's not zero, that G of Z is not zero
Oh, yeah.
at Z naught. Generally saying this will be the order of the pole. We may not use that information ever again. But that is like what you would say. Okay.
So this is a famous isolated. Like a very common.
Yeah, this will be your most general form of an isolated singularity, right? It says this is the same isolated singularity that gives you black holes. Right? Mass goes to, or the radius goes to zero. Gravity acceleration goes. Okay. Let's find some singularities.
Okay.
May just be Z plus or minus one.
You tell me?
It should be
Yeah,
Z
because-
plus minus one, because it's two fractions. you
It wouldn't
can
go to
take
zero.
function, and multiply the top and bottom.
That's undefined.
Yeah, so the denominator would be z minus one times z plus one. And it's already, then it would be, we don't care what the numerator is. As long as it's not like, g of like whatever value, like I guess one or negative one equals zero. Yeah, I think, let me work it out.
I mean, I'm not saying that you're wrong,
Right,
but what did we need here, right? We said that it's analytic everywhere except here z equals 0, and there's no other singularities. If there's no other singularities, it's isolated. If it's not, if there are other singularities, then it's not isolated. Do you need to rearrange it? I mean, you see it like right off the bat.
Yeah.
But do you need to rearrange it to be in that form?
No. I think so.
I was just like, making like year one.
it's like combine the fragments.
Yeah.
So I did like the one on the left, like times, like top and bottom, one plus, and then the one on the right times one minus e, so that they have the bottom would be the same.
Yeah. So what did you get instead?
So it was two z's over one minus e.
2z?
Yeah, I think it's just two. That kind of doesn't matter.
No, it doesn't. So this is why you were right, right? But I didn't want to give it to you right away because we need to look at what GZ is. So I said if GZ goes to 0 at the
Oh,
same time the bottom is going to 0, then it's not a singularity. So we need to make sure that it's in a similar form to this, right? Where you could say, okay, look at these poles. These are poles of order 1, right? The power is 1 here. And here, when z goes to either 1 or -1, the top stays a number. So that's a real singularity.
okay,
See the difference?
yeah,
But you're right, you look at that one, like, well, the first term is obviously blowing up. So you're right, like, this was a singularity and this was a singularity, and obviously if you add a singularity to a singularity. There probably are some circumstances in which we could get them to disappear, right? If you like had a plus and a minus, you could maybe get them to cancel out. But they need to go to infinity at the same time. Wanna try a harder one?
yeah.
Oh, y'all ready? All right, let's try this.
Oh,
If you do it, if you put in the form of, hyperbolic sine, and you hyperbolic cosine.
Okay, I like that. Hold on, one step at a time. Let me follow you. So let's do, you said sine over cosine?
Well, hyperbolic, yeah.
yeah,
So then whenever value of d that makes hyperbolic cosine equal to 0 is our goal, or r.
Is there a different way to write the sines and the cosines in terms of anything else?
you could write them as summations.
Oh, you could use Euler then.
Yeah, there's a nice little equality for hyperbolic sine and hyperbolic cosine.
Yeah, you brought sine was e to z e to the negative z plus two.
Yeah, I'm really going to do this to figure out what.
Yeah.
That's okay though.
So
So exponential of z,
minus exponential negative z
go,
divided by
what? Is that right?
I thought it was.
Okay, so what's next?
Then now it's gonna be divided by something like
No,
plus,
where?
it's e to the z plus e to the z.
Right. Okay, that looks pretty good.
Then now we can set the denominator equal to 0 and then find out what values of z. Make-
Oh.
Sure, yeah, I mean, you could just say. Right, when exponential z equals minus exponential minus z, right, that's a perfectly fine thing to say here.
Oh, yeah. Oh, wait, then so e to the negative z is just 1 over e to the z.
Okay.
What exponential of
E to the z,
e to the negative z is equal to 1 over e to the z.
yeah.
Yeah. But then it's just e to the z plus 1 over e to the z. Cancel
Not fully sure I'm tracking with that,
out. Okay.
You're
but.
talking about you set them equal to 0, and then
Yeah.
subtract one from, make them equal to each other.
Oh,
Is that
yeah.
what you're talking about?
Yeah, so like set the denominator equal to 0, so then e to the power of z is just equal to e to the power of negative z, and that's when you have that singularity.
Yeah, so that's one way to say it. We could use the definition here. Right, you could use the fact that there's multiple values, for example, in these exponentials. So you're saying this is equal to minus this, that's correct. But also every argument, right? Which includes the, 2n plus 1 times pi exponential that would modulate that argument. So multiple singularities, right?
Yeah, okay. That's when we have multiple poles.
Yeah, so you could just, maybe I'll let you find this for yourself if you want. Okay. You have multiple poles, and they're all found here. Is that true?
A bunch of these poles.
Every time. So each integer about of pi. Very good.
Yeah, so we have like a pole at pi over 2I, and then 3 pi over 2 I.
But also 2 pi over 2i.
Yeah, also 2 pi over 2.
Right. As long as n is an integer. And 0.
Yeah.
0 is an integer. So less obvious, but still there. Right? What kind of pole? Any guesses? Yeah, what's the order? Do you guys know? Maybe I'll leave that as a homework. Not homework, but for you to do.
Z,
I'll let you stew on that. Do one last example. What about this one?
when z is equal to 0, the top's also equal to 0.
Oh, that top's also equal to
Not
0.
a true singularity, like.
So it's not a true singularity. Good. This is an example of what type of singularity? This is a removable.
Oh, removal.
Yeah.
You're,
special. Okay, so this is a removable singularity, where is it?
At 0.
At 0, yeah, that's the obvious one, right? So Z naught obviously is 0 here. Okay. So it takes as an indeterminate form at 0/0. Right? Can we do anything with can we try to find out what the value is at 0?
0 divided by 0, 1.
Is it? That's a bold statement. Can you back it up?
But divided by itself. But okay, maybe give some, try not to.
So remember, the way that we want to find these things out tend to be by looking at them either through a different lens, by expanding them in powers, or by looking at them as a limit. Because one can go to 0 faster than the other, right? So how would I write this?
Be 1 plus power.
Yeah, we could write this as a power series, right? Just take the 1/z, we'll pull it outside.
Oh, you want the power series inside?
Okay, so it's every other one, it'd be the odds numbers, so,
So 1, 3, 5.
yeah, Z/1 minus.
Z/1?
1 factorial.
Oh, I'm just gonna do Z.
Yeah, Z. Yeah, Z, yeah, and that would be minus Z to the 3rd over 3 factorial. Plus Z to the 5th over 5 factorial.
Okay, that's it. Yeah. Good, so what happens? It's first term.
That's just, the first term is 1.
Good. What's the second term?
Wait, 1, you're putting it for going to 0 or no?
Well, we're gonna apply this, right?
Yeah, distribute.
We're gonna distribute.
Oh,
the Z,
you- okay.
1/z came out, right?
Oh, you're distributing it out.
Yeah,
Okay.
so we're gonna go term by term. We're assuming, yeah, sorry, this is poor math, right? So I should have written like that.
No,
There you
no, I just think, I thought we were going to 0, but you're right. No, that's true.
Applies there,
Yeah.
then this one applies here, and now you get,
Z squared over 3 factorial.
good. So on and so forth, right?
Yeah.
Okay, so now what happens is Z goes to 0.
You got 1.
0/0 equals 1. You knew it all along, but you didn't know how you knew it,
Right?
right? Okay, so that's right. This is an example of a removable singularity, and this is in contrast to the two that we saw before, right? So this one up here, you spotted it from a mile away. But what wasn't so clear was whether or not the top and bottom went to 0 at the same time. Right? This one here, hidden zeros. What is that made of? Right? And hidden zeros, multiple zeros. This one, obvious 0, but not a singularity. Cool. Questions, comments, concerns? Okay, so I don't think that, I mean, we could go directly into contour integrals. But I would say the next thing that we're gonna do is this complex integral section. And it's just like a brand new feel, brand new vibe. So I'll give you back, 7 minutes or whatever it is.
What chapter?
So this will be 24.8 in the engineering book, but in BOAS, you're looking just for complex integrals. Complex integrals, we've drawn this stuff. And it'll be really important for you to start drawing these maps. Because the power of the complex integral is using it to either avoid branch points, to avoid singularities, or to use some theorems that we're gonna find out about that equate different spaces, so that we could do an integral over, say, an infinite space, or so that we can integrate over a singularity by taking advantage of some of the properties of complex integrals. So they are going to be a cheat code for us to do things that you wouldn't normally be able to do in real math. Using real numbers, but then we'll be able to port those theorems into the real plane. If that makes sense. And that might just be words right now, but I promise it'll make more sense on Wednesday. Maybe. I hope. Actually, I won't make that promise. I hope that it'll make more sense on Wednesday.
Okay.
I will ask you to go to the SOTIs. SOTIs are out.
Yeah,
I don't think I have a single response for either class.
sorry.
No, it's not your fault. It's, what's that? A SOTI is like like feedback on the class, anonymous feedback on the
Oh,
class.
okay.
So apparently the department or the college really likes them. Department doesn't necessarily care. I prefer them because then I can see about how we can like change the class, make it better, but sometimes I get that from conversations with you too. But this is more of an institutionalized way so that you can give feedback to the dean. They can make sure that I either stay hired or get fired.
No pressure.
No, literally no pressure, right? Okay, so have a look at the complex integral section. We'll do that and if you get as far as Couchy's theorem, that's the one that is the valuable one. Couchy's integral theorem. I think we won't go as far as the Taylor and Ryan series. I think we'll transition after that to applications of complex variables. And so we'll look at them in the context of conformal transformations. We'll talk about Laplace transforms,
Okay,
Stokes equations, area integrals. There's all sorts of really fun computational methods
but it's in the complex.
in the complex plane. Okay, comments, questions, concerns? Cool.
Thank you.
Hey, my computer didn't even die.